Hi, I'm Dan Zanoble, and this is a personal project I've been working on to continue building my skills with ROS2 development. For this project, I aim to recreate the final project from a previous class as a ROS2 Webots simulation and practice driving actual robot hardware from a Raspberry Pi with another ROS2 package. ENPM 701 Autonomous Robots was a class I took last spring as part of my master's program in robotics. Throughout this class, we assembled a skid steer robot powered by a Raspberry Pi and programmed it to autonomously grab colored blocks. The final project for this class, worth 10% of the final grade, was known as the Final Challenge. The goal was to program the robot to autonomously retrieve 9 colored blocks in a specific color order and drop them off in the construction zone. Points were awarded for every block delivered. Concepts like object tracking and path planning were really important here, because any blocks that got knocked over would be impossible to retrieve. It was also really important to track the robot's current position as accurately as possible, because contact with the walls was an instant DQ. If you've seen my previous videos, you might remember that my final challenge attempt ended in minor disaster. I had a pretty basic path planning algorithm that always went for the closest target block currently in view. It got hung up when 2 red blocks were a similar distance away. When it turned towards the one that looked closer, the change in perspective made the other one look closer, so it would turn towards that one, and so on. This went on back and forth for about 10 agonizing minutes, which was ample time to reflect on my life and the dark path that had led me to this accursed place. I wondered, were the hours upon hours I sunk into this project all for nothing? Was I doomed, like Sisyphus, to watch in despair as the boulder rolled back down the hill? Anyway, I'm totally over it now, but I felt like revisiting this project would be a great way to practice simulation and hardware control with ROS. The original programming was just done in a single Python script and always tested directly on the robot. I think the ROS package plus simulation is closer to what's done in real-world robot software development. It's also an opportunity to implement a much more robust path planning strategy. I decided to build a Python package instead of using C++ like I normally would. This made it easier to borrow old code from the original project. I used the Webots proto system to model a custom robot, blocks, and arena. The robot has a camera, gripper, IMU, 4 wheels with skid steer controls, and 2 wheel encoders, just like the real robot. The arena is 10 feet by 10 feet with a 2 by 2 foot starting area and a 4 by 4 foot construction zone. On launch, a script populates a YAML file with XY positions for the 9 blocks, with restrictions that keep the blocks at least 2 feet apart and outside of the construction or landing zones. The launch file reads from the YAML file and writes the info into a temporary world file, so you get a randomized block placement every time. You can also turn off this randomization by setting randomized blocks launch argument to false, which is useful for troubleshooting. I started this project off with a series of testing and calibration nodes. I used a teleop node to confirm movement, grip functionality, and test the functionality of the other nodes. The color picker node lets you tune HSV masking values in real time. The bounding boxes node was for troubleshooting block detection and logic for ignoring false detections. The distance calibration node is for quickly gathering data for calibrating block distance estimations based on bounding box height. The finished final challenge routine uses 4 nodes: the robot driver, a block tracker node, a path planner node, and a final challenge node. The driver subscribes to CMD-vel and CMD-grip topics for driving the wheels and gripper, and publishes the wheel left and right angular positions. The block tracker node subscribes to the wheel position, IMU, and camera image, and publishes the robot's current X, Y, and theta position and a marker array with the block colors and positions. A marker array is a very useful message type from visualization messages that holds position, orientation, color, and namespace information about an array of objects. The path planner node subscribes to the robot position and block marker array and sets up a path planning service. When called, the service returns a path type message from nav messages using an A-star path planning algorithm. Lastly, the final challenge node subscribes to the robot position, block markers, and camera image, and publishes to the wheels and gripper per the behavior of its current state. These states are: scan for blocks, the robot turns 180 degrees, letting the block tracker build a map of the block positions; go to block, the robot plans a path to the goal block and travels along it until about 1 foot away from the block and facing towards it; align with block, The robot uses camera image to move towards and align with the block until it's in the gripper range. Grip block. The robot closes the gripper and waits 1 second for the block to settle in place. Go to drop off. The robot plans a path and travels to one of 3 drop off locations depending on block color. Align with the drop off. The robot turns to face north and moves forward to the drop off point. Release block. The robot opens the gripper and waits 1 second for the block to settle. Back away from drop off. The robot backs up from the block by 1 foot. And repeat. The robot cycles through these states until all 9 blocks are acquired. Overall, I think making a ROS simulation was a great way to approach this problem. The different nodes and topics make it easy to manage continuously updating data. Being able to easily reset, randomize block positions, and rerun the same exact starting conditions made troubleshooting much quicker than when I was manually getting up and resetting it every time. I also didn't have to sacrifice my whole living room to get the 10 by 10 foot space. The biggest improvements over my previous attempt were the block tracker and the path planner. The block tracker uses block distance estimation and the current robot position to estimate block XY positions, but there was a lot that went into preventing it from logging false detections. If a block is detected within a certain radius of an already logged block, it's merged with the old block and the positions are averaged, so over time the estimate will become more accurate. You can see this happening on the map here. Preventing false detections was really important, so detected blocks were ignored if predicted XY position was outside the map bounds, in the landing zone, or in the construction zone. If the block was not fully in frame, aka the bounding box centroid was too close to the left or right side of the frame. If the block was detected for less than 5 consecutive frames, or if the bounding box area was too small. The path planner required less troubleshooting. As long as the block positions were accurate and a reasonable buffer zone was set around the blocks and walls, it was able to successfully navigate the robot. It always chooses the nearest block, but since block positions are based on stored values rather than what's currently in the camera view, there's little chance of the closest block position switching back and forth like it did before. With the simulation done, I've started with the hardware implementation. I installed Ubuntu 22 server on the Raspberry Pi and have a driver node, a teleop node, and a color picker node. The driver node converts the different topic messages to Pi GPIO commands, meaning if I set it up right, my simulation nodes will also work on the hardware, a good example of hardware and sim parity. Since I'm running headless, I also have a node for seeing the camera image using Foxglove. However, I noticed there's a crazy amount of lag. Not sure if that's a bandwidth issue because I'm connecting through my iPhone hotspot or something else, but the delay is significant. I'll keep messing with the hardware, but I probably won't go all the way to rebuilding the full-scale final challenge. I've already met my goals. I'm confident in my ability to simulate and drive actual hardware using ROS packages. This was a very fun and informative project for me. Thanks for watching.